Thank you for an excellent presentation, Jeff. I should say that there was a time when we weren't sure Jeff would be able to participate in this workshop because he was born in Canada. Um, so with that, I'll introduce our next speaker, who is Glenn Morrison. Glenn is a professor in civil architectural and environmental engineering at the Missouri University of Science and Technology. I've known Glenn for a very long time. I know he's passionate about this subject. And if I could summarize Glenn's passion anyway, I'd say he wants to make America's indoor air great again. So Glenn, take it from there.
Thank you, and I hope I get your donation soon. Thank you. Today I'm going to talk about indoor chemistry and aerosols, and specifically I'm going to talk about transformations, not necessarily the composition per se, but the transformations that take place and how those influence indoor aerosols. I'll be talking, there's many things that can influence indoor aerosols shown here. But I'm primarily going to be talking about oxidation. So in the atmosphere, one of the most well-studied processes that occurs in the atmosphere that can generate aerosols is the reaction between oxidants and volatile organic compounds. These compounds here are actually in a class called terpenes or terpenoids. These are the primary oxidants in the atmosphere that can react and generate a wide variety of molecular products. Those products are oxidized, kind of sticky, polar, and so because of that, they come together. I guess I can point over to this slide here. They come together and they can nucleate new particles or grow and condense onto existing particles. And ultimately what you get is this collection of particles known as secondary organic aerosol, overall increasing the mass of aerosol in the atmosphere. Now, in outdoor environments, one of the drivers of this chemistry, one of the main drivers of this chemistry is the sun. And during the daytime, each of these, the sources and the mechanisms that occur in each of these boxes can be influenced by the sun to a great degree. In indoor environments, this is a little bit different. The sun doesn't penetrate into the indoor environment nearly as much, orders of magnitude less irradiance indoors. And there are other differences. By being in a box like this, the sources and sink characteristics are very, very different. Buildings are inherently low sunlight intensity, but the aerosols that are generated by this chemistry actually spend a lot less time indoors, and so are relatively fresh. They're younger because ventilation, ultimately their age is on the order of an hour. Indoor surfaces are very important, as Jeff pointed out, specifically for aerosol deposition, thereby lowering the mass concentration of all the aerosols indoors, but also by removing precursors or actually forming some of the precursors that are contributing to aerosols. The precursors themselves are strongly influenced by the indoor environment. One of the most important sources of terpenes is us and the things we do: cleaning, solvents, scented products, food. All of these things release a great load of terpenes into our indoor environment. And so the concentrations are much higher indoors and outdoors. And not only that, the composition is very different because of the products that we use indoors. The oxidants themselves are driven primarily by ozone coming in from the outdoor environment, but the concentration is generally lower because of reactions on surfaces. So surfaces reduce those concentrations. But the concentrations of the nitrate radical and the OH radical are more complicated. They're generated by chemistry indoors and also removed by various sinks indoors. But overall, the chemistry is similar but not identical to outdoor environments. We've seen lots of papers that show that secondary organic aerosols are generated indoors. This is just one example from Sarwar et al., actually Rich Corsi's group, a few years ago, in which in a room with elevated ozone, here, relatively elevated, they introduce an air freshener, and you see a really rapid increase in the concentration of particles, submicron particles here, that persist over quite a long period of time. But one thing they point out is that the concentration is quite a bit higher than the outdoor ambient air quality standard, which is, I think 24 hours, I think is 35 micrograms per cubic meter now, down in this range. So it's not just that we make them at very high concentrations, depending on the conditions. This is one example from a recent paper showing that painting can do the same thing, and there's many papers like this. This shows, just to describe this figure, you have time here. This is a particle diameter, and the color represents the concentration, the intensity of the color. So you see is this introduction of these paints, the growth and persistence of aerosols that are about 100 microns. So this is very well recognized process. So that's what we know about the secondary organic aerosol formation generated indoors. I'd like to talk more about what's emerging, what we're learning now about the chemistry taking place indoors and how this influences potentially secondary organic aerosols or other aerosols. The areas where I think that we're really learning a lot more recently is in measurements, measurements, modeling, the influence of the building, occupancy, and actually sunlight is actually coming back into vogue, actually can be important in certain circumstances. So in measurements, one of the advancements we've seen is the application of derivatization techniques to expand our understanding of the composition of aerosols generated by this chemistry. This was a paper in which they did some house cleaning, and the house cleaners release terpenes, which react with ozone. And the products you see here are just a few of the products that they analyzed and identified and quantified, not just identified, but quantified in the aerosols generated by these events. In modeling, so indoor environments are a box. That's generally how they're considered in models. And the model that they put in that box is basically the same as the model that we use for outdoor chemistry. Those are very advanced models, but the difference between outdoor environments and indoor environments are things like surfaces, very important, and the composition of the precursors, the reactants. And so this is a paper by Carslaw in which they try to incorporate at least some of those differences into the model, and they show that as one example of an outcome, during a cleaning event, they expect to see a lot of peroxides generated during that cleaning event in the aerosols themselves. But they also recognize that the model is very sensitive to the inputs, and there's still a great deal of uncertainty in the ability to use these models to be predictive of not just the aerosol's mass concentration, but also the composition. In that vein, I wanted to mention this paper by Khurshid et al. The peroxides that are generated in these events can be measured or recognized as a reactive oxygen species, which potentially can increase oxidative stress in cells. And so in this particular experiment, they introduced high ozone and high terpene levels to a test house. And let me know if I get anything wrong. And what they found was here that under those conditions, they saw a much higher ROS composition or concentration than outdoors, and sort of consistent with the idea that a lot of peroxides are formed in these cleaning events. Also, Phil Hopke and the group there at Clarkson also have seen these ROS species being generated. Building operation. We've heard a lot about buildings and building operation from the others, but I just want to mention one thing that's specific to chemistry, and this is from Yusufi and Waring very recently. In experiments, they essentially have a terpene and ozone in the same chamber. They change the ventilation rate, and what they see is interesting in this case, that the peak secondary organic aerosol concentration is influenced by air exchange rate, or is it? For pinene, not so much, but for limonene it is. So there's a lot we need to know. We still need to know about how buildings influence this chemistry. This is fascinating. Ozone can react with compounds that are adsorbed to surfaces, or just on surfaces, generate products that leap from the surface and somehow nucleate new particles. This is really fascinating because this is a paper by Waring that showed this with terpineol, This is a paper from Sleeman that showed that this reaction can take place with nicotine and generate a distribution of nucleated particles above the surface. And these reactions can be very, very fast, much faster than in the gas phase or what you would anticipate happening in the gas phase. And what's fascinating is that if this is happening, that means that a lot of the products of the chemistry taking place on surfaces can be transferred to aerosols. And I'll mention this again a little bit later, but, or at the very least, being transferred to dust that can be resuspended and inhaled. Occupancy, a very important factor, as Dr. Weschler has shown in the past few years. We are very reactive. Our skin is comprised of skin cells that have a lot of skin lipids in them, that have compounds in them that react readily with ozone in particular. These cells are constantly being shed, and we shed a lot of skin cells in indoor environments. And so we coat all the surfaces in our indoor environments with us. And what we've coated it with are compounds like this. This is squalene. And I note, Charlie, that I missed a double bond in this when I drew it. Sorry about that. And that's the point. There's so many double bonds, it's easy to forget one. But the double bonds are important because they react with ozone, very rapidly with ozone. And so if that's true, all these surfaces here that are coated with us will also react with ozone. That's one probable reason why our indoor environments are so reactive and why indoor ozone levels are lower. It's an important oxidant that contributes to secondary organic aerosol, and therefore that's important. But not just the surfaces, we are also covered in our own skin oils, obviously, and so we react. There we go. We are actually removing ozone from our environments. And this was shown very clearly in this paper by Ph.D. et al., in which you see two experiments here. The solid lines represent an experiment in which they introduced limonene and ozone into a room, and as expected, the ozone concentration would rise as they were introducing it into the room. The limonene concentration rose, but also the secondary organic aerosol concentration rose, and that's this red line here. Without anybody there, that's what you see in the solid lines. They do a second experiment in which people enter the room. When they enter the room under the exact same conditions, the ozone concentrations are much lower. That's the dotted line here. And the resulting secondary organic aerosol concentrations are lower because there's less ozone to react with the limonene. So we see occupancy, the building surfaces, all of these things are very important. Now let's get back to sunlight. This is a really interesting finding that came out just a couple of years ago. When we cook, when we generate combustion byproducts indoors, we generate NOx, nitrogen oxides, a variety of them. NO2, when it's released by a cook stove, for example, can stick to surfaces, react with water, and generate nitrous acid. Now, what Alvarez et al. Showed was that the sunlight that can come in, the visible light that can come in through a window can enhance the rate of this reaction, especially on certain organic surfaces like cleaners. If you have a surface that's coated with a cleaner, it can enhance this rate so you have a lot more nitrous acid produced. Why does this matter? We haven't talked about nitrous acid yet. Well, nitrous acid is volatile. It will go into the gas phase and photolyze, and it photolyzes into this important OH radical, which is one of the oxidants that's important in producing secondary organic aerosol. What they found that was near windows, this OH concentration was of the same order of magnitude as what you see outdoors. So clearly, at least in some areas of the building, we can see a very high, potentially high oxidation rate or of OH with organic compounds. And OH is interesting because it's indiscriminate. It doesn't just react with terpenes, it reacts with a whole suite of other volatile organic compounds. Okay, so knowledge gaps and opportunities. So I'd say that for me, there are many, many knowledge gaps, and I think some of the folks here have discussed some of them in great detail, and I'll try not to overlap too much with those, but for chemistry, I think one of our greatest opportunities is field analysis. The instrumentation available for outdoor ambient measurements, they put them on airplanes, they fly them around. It's amazing what they have. Almost none of that has ever really been used indoors. until very recently, we only saw one of the first papers on an aerosol mass spectrometer used indoors. Very recently, the phage instrument was just the past couple of years, and we've yet to see direct nitrate level concentration measurements indoors, unless it came out in the past month or so, and I missed it. And so there's a great deal we can learn, and this is just an example down here. This is right here is actually a filter sample that was analyzed with a high-resolution mass spectrometer. That sample is of secondary organic aerosol generated under a particular set of conditions, and I borrowed this because I wanted to show you how many peaks there are in that analysis. There are hundreds or maybe thousands of different individual compounds that are generated in this chemistry. We can't possibly know what all of those are, but if we start with the kinds of instruments we have, like this, we can, start to see the kinds of differences of the chemistry that happens indoors, and start looking at how human activities influence these by looking at the elemental composition that we can get from these analyses. There's some great output from these models, or from these instruments, that I won't show here, but you can learn a great deal about the chemistry from those instruments. Models. Right now, the models that are being applied are much better than they were even just a few years ago, but they still are missing quite a bit that's unique to indoor environments. The basic chemistry is there because we've got that from the outdoor, decades and decades of outdoor chemistry work. But we really need to better account for the surface phenomena that are taking place, the building characteristics, occupancy, activities. All of these things are, I think, poorly characterized. Just a couple of examples of surface phenomena that could be important. So consider the surface as a film, okay, a film that coats all of the paint and all the carpet. There's this little film of organic and salty material that can be influenced by pH, and that pH is influenced by us. And it's influenced by us because we're generating CO2. CO2 is an acid that can decrease the pH of water films, but also, and so the CO2 concentration in here is much higher, or can be much higher than it is outdoors, whereas the ammonia concentration can also be much higher, and that's because of cleaning activities, because of the emissions from dirty diapers and cat boxes. There are plenty of ammonia sources that can increase pH, and that affects the rate of hydrolysis. It affects the rate of many chemical reactions that ultimately can influence aerosol composition and formation. The surfaces themselves are aging, and it'd be great to understand how these indoor surfaces here are influencing the composition of aerosols by transferring compounds back and forth. One example here is, this is a paper by Sleeman et al. From 2010, in which they show that nitrous acid reacts with nicotine to generate nitrosamines, carcinogens. So toxicants that are generated at surfaces, it would be very interesting to understand how much of that is transferring to dust that we inhale, or transferring to aerosols by just direct transfer. Finally, buildings. Jeff made a great point about buildings. He talked about heterogeneity of the inside of the building, how we look at one place versus another instead of it being a box model. By heterogeneity here, I mean the fact that every building is different. We have all these different kinds of buildings, and two buildings that were built identically, side by side, are going to be very, very different when you get down to understanding the chemistry. And so integrating measurements from those kind of buildings into models is very, very challenging, just because the occupancy, the air exchange rate, local composition of the air around a house, all of these things are going to be significantly influence our ability to compare models to measurements. Air paths, interstitial spaces, I won't mention more about that, very important. And ultimately, because this is so complicated, we're going to have to be able to identify what parameters are really most important in modeling, ultimately, so that we can take the chemistry that we understand and the building science we understand to extend that to exposure. And that's all I have today. Thank you.